Hello, everyone. Welcome to pay attention to our work about optical flow estimation, seeking optical flow from geometric matching consistent perspective. Recent deep learning-based optical flow models have achieved considerable success. However, these models often train networks from scratch on standard optical flow data, which rejects their ability to robust and geometrically match image features. In this paper, we propose a reseeking to previous optical flow estimation. We particularly leverage geometric image matching as a pre-training task for the optical flow estimation with better visual representation. As GIM shares some common challenges as the optical flow estimation and with massive labeled real-world data. Thus, matching statistical scenes capable to learn more fundamental feature correlation of objects and scenes with consistent displacements. Specifically, the proposed matching flow model employs a Cauchy attention-based network pre-trained on megadepths to extract coarse features for further flow regression. Extensive experiments show that our model has greater cross-dataset generalization. Our method achieves greater error reduction from GMA on syntax clean paths and KT test sets. Codes and models have been released in here. Recent optical flow estimation models often train networks from scratch on standard optical flow data, with a matching model to capitalize the features of different images. This motivates our work of providing the seeking to the importance of geometric image matching to the optical flow estimation. In particular, geometric image matching shares some common challenges with optical flow estimation. Secondly, it's much easier and simple to collect the real-world GIM data. Lastly, we aim to provide a reseeking of a general training pipeline of our model training pipeline is shown here, which is composed of FME and OFE. For stage 1, we first train the FME on massive real-world GIM data to learn statistical scene matching caused by viewport change. Thus, given a pair of images, the cost for decorrelation volume can be achieved with matrix multiplication. For stage 2, we follow GMA and jointly fine-tune the FME with the specialized optical flow estimator to get the final displacement field. Stage 2 is gradually applied on Flancher Flancine 3D, and such a progressive pipeline makes the match flow just intractable object motion within complex scenes. For the pre-training, we apply the dual softmax to the correlation volume and get the probability before the optimization. Our loss function LC is a negative log likelihood. As for the optical flow loss, we supervise our network use L1 loss following previous work. We utilize MACDEPS as our matching data set and train the feature encoder. We then follow the standard training pipeline of further training our model on Flancher and Flancine 3D. Then we fine-tune our model use data from clean and final part of Syntax, KT, and HD1K. Here are the qualitative results. Compared with GMA, our match flow can successfully recognize the small signage in the first image and reduce the flow leakage around the car boundary in the second image. On Syntax, the flow estimation from match flow exhibits clear detail and captures small and fast-moving birds in the third row. These results show the effectiveness and superiority of our GIM pre-training. Besides, we evaluate the generalization error on the Syntax and KT training set after training on C plus T. As shown in the table, MatchFlow achieved greater error reduction in average endpoint error and flow all based on GMA or RAPS. This result indicates the greater generalization performance of our method. For the test set, MatchFlow also improved the results of GMA or RAPS a lot. We also provide several application studies of our components. We first validated the benefits of GIM pre-training. The number of tension blocks and tension type are also important. Apart from this, we conduct more ablation on KT, as KT on the much smaller aspect ratio, and we finally use bilinear interpolation to adjust the resolution with the TILE technique for better performance. To determine where our gains come from, We use occlusion map provided center on the training set to divide the image into occluded and non-occluded arrows. Use a model trained on offline scene 3D. When evaluate its on 3 random parts of center as shown in the table. A relative improvement of our method compared to GMA is mainly attributed to the error reduction within the non-occluded region. We further visualize the correction volume on 100 center final pass images. The first row is for GMA, and the second row is MatchFlow G. The much higher central value of our method validates that GIM pre-training can benefit the optical flow envelope, especially within the non-occluded region. We further supply a combination of generation arrow to depth steel self-supervised pre-trained dyno feature and a class supervised twinless VD feature. Our method still performs better among them in more complex center. In contrast, depth still greatly benefited from less dense matching based flow training on Kitty, while greatly degrading the results on center. Finally, we show the computational overhead of our model in the table. The overall computational overhead of MatchFlow is modest compared to FlowForm, while our performance is still competitive. All in all, this paper proposed to use geometric image matching as a printing task for learning more robust matching features for optical flow estimation. Share some common challenges with optical flow estimation while with much more real-world data. Geometric image matching pre-training can help learn fundamental feature correlation of scenes. To improve feature matching in Character, we further proposed adding static culture attention layer for self and cross-attention learning. Real-time equilibriums show greater cross-dataset generalization and superior performance of our method. Future work may focus on reducing the attention layer in feature matching retractor while preserve competitive performance. That's all. Our codes have been released. Thank you for your listening.